Yesterday, we talked about the difference between the an object being pulled up and an object being pushed down, and how that actually affects the force of friction. So if you're taking an object and you're pulling it up, that actually lowers the amount of friction because the normal force doesn't have to work as hard. If you're pushing down on the object, that increases the force of friction because that means that the normal force is actually greater because you've got two forces pushing down. You've got mg and you've also got the force of the person pushing down as well too. So that counts as two extra masses or two extra forces that go along with it. So I think we're pretty much okay with that one. We're going to try to keep going with the stuff that we're doing. Let's see here. We did do where we did work against gravity, right? So we lifted an object up. Okay. Where it goes down? Yeah. Okay. Um, good. So let's see. There are special cases to where we can actually have no work being done. We mentioned a couple of those, like one, if you're pushing straight down on the object, then the angles are at 90 degrees to each other, and 90 degrees is bad because in that case, no work is actually getting done. So, for example, we did the one where we're pushing down, but let me show you another one too, and this one's actually really tricky. If you're moving across a floor and this box gets pushed across the floor at a constant speed of 10 meters per second, technically in this case there is actually zero work being done. Okay, because the reason why is because there's no acceleration, and if there's no acceleration, technically there's balanced forces. Okay, so right. And there are a couple of ways to interpret this. Okay. Um, One way that we can actually interpret it is that one, zero work is being done because there's no acceleration. So if you've got force times distance, this force is equal to zero, and zero times anything is just zero. So you could say that 0 joules of energy has been expended. But that's also like a little bit short-sighted because if you think about it, the object is actually moving. So yeah, this concept of just something moving at like a constant speed would be an ideal thing if there's like no friction involved, if it's a frictionless environment. Okay, so I'm sorry, not no frictionless, no no frictionless, no friction, right? So if there's no friction, or if it's a frictionless environment, that interpretation works really well because you can say that well, there's no other forces acting on it, an object in motion stays in motion, so therefore it's just going to keep going. On Earth, that's really hard to interpret in real life. If you're in space, that's actually pretty easy to interpret because if you take an object in space and just like push it, once it leaves your hand, that object just keeps going in that straight line value until well for it until it hits something. Yeah, so a really really long time away. It basically is out of your control at that point, quite literally. Another way to interpret it is if it's on Earth, you can say that the amount of work being done is being counterbalanced by the amount of work being lost due to friction. So another way to think about it is same floor, same box, but if it's going forward, I'm going to draw the arrow up here this time because I'm going to put force arrows down below. Let's just say that you've got a force pushing this way at 10 newtons, but the force of friction back this way is also 10 newtons. So in this case, there are forces applied to the object, but there is no acceleration because the force to the right and the force to the left end up canceling each other out. So if the force to the right and the force to the left end up canceling each other out, we would say that the sum of the forces is equal to zero. We would say that, okay, well, yeah, there's things acting on it, but it's still moving at a constant speed. So the amount of work that we are doing with the 10 Newton force is being canceled by the force by the work that we're doing with the friction. So we'll consider to the right positive just like we normally do. So I would say that, if this is 10 newtons and let's say that it covers a distance of, I don't know, let's just keep it easy, 10 meters. Okay, so like 10 times 10 is 100. So if we add up the two works put together, there is 100 joules of work. 100 or 10 newtons times 10 meters makes 10 newton meters, which would be 100 joules. There's 100 joules of work going this way, but there's also negative 100 joules of work being added this direction. So when you add them together, that comes out to be 0 joules of work, and which is why I like to say 0 work being done and not no work being done. Okay, and the reason why I say 0 work is because there is actually a transfer of energy happening here. And if I said no work, you start immediately thinking in your brain that no means nothing's happening, but something is actually happening here. It's just that the work being done is being counterbalanced by friction. So I like to say 0 work and not no work. Does that make sense? It's just a little sneaky thing that I like to try to do. Okay. So you got to remember that it's like a number. It's like you're balancing your checkbook. It's like what? OJ, yeah, zero joules, yeah. Do I need to fix that? Like people in their notes are like, OJ, what's going on here? There you go. How about 0 joules? Okay, 0 joules is going on here. 100 joules minus 100 joules equals 0 joules. So this is a case to where you can get no work or 0 work being done, even though there is actually forces acting on that situation. Okay, the 90-degree rule also still applies as well too. Let's see here. We've done this one where we actually increase or decrease the normal force. We've done, let's see here. Um, Oh, I guess another one, which this one actually kind of makes sense. If you don't actually cover distance, then technically 0 work has been done. So you can take an object if it's like really, really, really heavy. So like just say that this is like a giant stone block and it's like, I don't know, 500 kilograms. That's like over 1,000 pounds. You really can't take this object and like push it across the way. Does that mean that you can put a force on it? Absolutely. So like you can push this with a force of 500 newtons, but it's not going to go anywhere. So just because you're pushing on something doesn't mean that work is going to actually be done. In order for work to be done, there has to be motion involved as well too. So this is I have a force, but there's no distance that's actually being covered. So if the distance is 0, then that also means that 0 work will be done because there's no distance that's being covered. So if this doesn't move at all, this would basically be your force times 0 meters, and the force times 0 meters is going to come out to be 0 or 0 work being done. Okay, so that would be 0 joules. We get our OJ again. Okay, even though you're putting a force on it. If you're putting a force on it, that does not mean that work is being done. If you are moving, that does not mean that force is being or that work is being done. In order for work to be done, you have to do force times displacement. And that displacement has to be a non-zero number in order for work to be done. Okay? Um, and then there's also, because things can get even weirder than that, because technically you can not do work by just going back to your original location. So that's also a thing. I thought that would let me go down. Oh, no, guess I got to use the mouse. All right, I'm going to switch over here. So, like, if you start off here and you've got an object and there's like 4 different positions, and you take an object, let's just say that this thing has a mass of 10 kilograms, and you take the 10 kilograms and you push it over here, and then you lift it up in the air, and then you carry it back over here by pushing it, and then you move it back down. Well, since you made it right back over here, there's a couple of different ways that you could do this. You could count the individual works that gets applied, and you could say like, okay, well, you did work going this way, you did work going this way, you did work going this way, and you did work going this way. So I could add up all your works together, and then whenever I add up all of the work being done, I could find out what your total is. Just keep in mind that if you go in the opposite direction, that counts as a negative, okay, because you're actually spending that energy instead of using that energy. So instead, though, the total displacement of this entire thing is 0. So since we made it right back to where we started at, our displacement is equal to 0. So therefore, the work being done is equal to 0 work being done. Okay? You don't have to do that problem. If the total displacement in any direction ends up being 0, your displacement is 0, and by definition, you have done no work. Okay? Once again, that doesn't mean that you didn't exert any force, and that also doesn't mean that you didn't go anywhere. That just means that by definition, no work was done. So like just taking a box and just dragging the box around in four corners, if you make it back to your original position, technically no work is being done. When you do a push up and you start off on the ground and you push up and then push back down, did you exert force? Yes. What was your total displacement? 0. By definition, 0 work was being done, which is weird. Do what? Ooh, how's that like from a physics perspective, how is that helpful? Okay. So like from an engineering perspective, it is. It is. It is helpful, okay? Because in real life, you actually do lose energy in the process. So, in terms of work being done, you want to be able to calibrate. So, like from an engineering standpoint, if you're making an engine, you want the amount of motion and the amount of force to be able to go back to its original place to where the force on it or the total work being done at the end is equal to 0. So, like a four-stroke motor, for example, each part of the cycle has to make it back to its displacement of 0. If you have the forces unbalanced in any particular part of the stroke, because it's not just one movement, right? It's actually a series of movements that get put together, and all of those movements need to make it back to have a total work of 0. You can calculate the forces that are involved in the engine, find the displacement between them, and then get it back to 0. Okay? That would be a theoretical number. The engineers would then take it and tweak those numbers because, theory and practice work completely different from each other, but it'll at least get you close. You know what I mean? It'll get you a close value, and then you can take it and be like, that's tweaking the numbers. Pressing buttons is totally counts as tweaking the numbers. Yeah. So I mean, anything where you want the thing to go back to its original location, technically is taking advantage of this total work equals 0 concept. Um, Now, in real life, anything that you're going to lose energy due to friction. So there's always going to be this net loss in real life. So technically, everything doesn't actually equate to 0. There's usually always going to be some loss due to heat or friction or something like that. Okay. Um, so that's the only thing that I can think of as to why it would actually use that. Um, there's also some if you're dealing with field forces, you can use that trick as well too, and it's also useful. There is a particular thing in calculus called Green's theorem, which applies to fields, and it's a little bit above our pay grade, but it uses this trick as well too, and it's useful. But I don't think we necessarily need to go into it though. All right. So let's see here. Um, I think we're almost ready for. I'm going to give you one more really important thing. Uh, Work and kinetic energy are related to each other, and we're pretty much okay with kinetic energy, I think. So I don't think I have to go into a whole lot of detail about it, unless y'all really want me to. I'm going to assume that you guys know that kinetic energy is the energy of motion, and that it's equal to 1/2 mv squared. Um, So I'm going to just say they're related to each other. I do probably need to say that since the kinetic energy is equal to 1/2 mv squared, it is impossible to get a negative number for kinetic energy. So that's actually something that you might not have learned in physical science, but you can't have a negative because even if the velocity is negative, a negative times a negative comes out to be a positive. So anything that is in motion, the kinetic energy is always assumed to be a positive number. Negative kinetic energy is not really how we do things. Okay? So if anything has motion, it has a positive kinetic energy. That kinetic energy can be spent. Um, so if you have no motion whatsoever, that's the only case where the kinetic energy can be 0, but you can't have a negative kinetic energy because if it's moving backwards, it just goes the other direction. There are very specific reasons why we do it this way. Um, one of them is like temperature. Like you can't have a negative temperature for the same reason that you can't have a negative kinetic energy, because the measurement of temperature is the ability of things to actually move around. And if you have no motion, technically that would be a temperature of absolute zero. Okay, so, and I should probably specify that it's absolute, like you can't have a negative absolute temperature. I know you can have a negative degrees Fahrenheit or a negative degrees Kelvin, but those are just scales that we use. That's not an absolute scale. The absolute scale, 0 Kelvin, means that like nothing is moving inside that object whatsoever. All of the atoms are just like completely and totally still. And that applies there as well too. So you can't get a negative for temperature, and the same reason that you can't get a negative for kinetic energy as well too. Because if it goes the other direction, technically it still has energy. Okay. Hopefully that makes a little bit of sense. Um, all right. So and work and kinetic energy are related to each other. So much so that like you have to do work to get things to move. Okay, there's no way around that. You must do work to get things to move. So, in order for you to spend energy, you have to do work. Okay, and how we're going to write that is we're going to write it this way: the work being done is equal to the change in kinetic energy. Okay, the work being done is equal to the change in kinetic energy, and you can also write that as the Kf, the final condition of the kinetic energy, minus the initial condition of the kinetic energy. A good way to write that is, if you've got a bullet and the bullet goes through the wall and it slows down after it hits the wall, before you could say that the kinetic energy of this was equal to like 1500 joules. And then afterwards, after it hits and it smashes through the wall, what would the kinetic energy of the bullet be? Let's say that it goes down to 500 joules. Okay. Then, if this is the case and it goes from 1500 to 500 joules, we can safely say that the wall did 500 joules of work. Oops, no, I lied to you. I'm sorry. I can't do I can't do math. What is the final minus the initial? It's 500 minus 1500, so negative 1000 joules of work on the bullet. Okay? And you can have, like, the change in kinetic energy can be negative and the change in kinetic energy can be positive, but kinetic energy by itself can't be negative. So, like, what this means is that the wall just made a deficit of energy on the bullet, which makes sense because it lost 1,000 joules of energy. If it loses 1,000 joules of energy, it goes from 1,500 joules to 500 joules. Then that's going to be negative 1,000 joules of work on the bullet itself. Okay? Does that kind of make sense? You okay with that? Okay. Um, good. Good, good, good. Let's try and see if we can do something. I'm going to try a problem. All right, let's see if we can do this one. This one involves like calculating the work done by lots of different forces. You need to push a box of supplies up a ramp. So I'm going to make a ramp here, and I'm going to put a box of supplies on said ramp. And we're going to try to take this and we're going to move it up. The weight of the box is equal to, so I'm going to write this out to the side. The weight of the box is equal to 225 newtons. Okay. And let's see here. The distance of the ramp is 6 meters, and it's going to be going up a 5-degree incline. So the distance is equal to, that's weight. Let me rephrase. How about force weight? How's that? FW? It's going to be 6.0 meters, and the angle is going to be 5 degrees for the incline. Let's see here. You exert a force of 85 newtons parallel to the incline, and a 56 Newton kinetic friction force is exerted on the box by the ground. So I'm going to go ahead and add these forces over to the side. We're going to say we're going to push up the ramp like this with a force of 85 newtons. And we have a force of 56 newtons of friction going backwards. It's going to be 56 newtons back this way. Okay. All right. I think this is all the information we need. We're going to say, all right, going up this ramp, let's calculate how much work we do on the box. Okay, so the first question is going to be, how much work do we do on the box? Yes, we do on the box. Okay, we know that for this entire ramp, I'll go ahead and draw it out like it's a right triangle. We know that the angle here is 5 degrees for the incline, and we also know that the distance up here is 6 meters. So I'm going to write that out as 6 meters as well too. So we're going to ask ourselves, how much work did we do on the box? How much work did we do on the box? What would we do? Let's call it, I'm going to call it work U. Okay, what's the force? Because this is going to be F D cosine theta. We are asking, how much work did we do on the box? How much work did we do on the box? That's the only thing that matters. Okay, right. So so how much work do we actually have going here? Okay? Because this is the direction of the motion is up the ramp, right? So the force is up the ramp. The 85 newtons is up the ramp. Not yet. No. No, 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 no. Not yet. Because here's the deal. Okay, I asked how much work are we doing on the box. I did not ask you what is the total work done. Yeah, I didn't ask how much work was done. I specifically asked about the just us. Said how much work do we do on the box? So if there's a person pushing, what is the work being done by this force specifically? So that's going to be 85 newtons times 6 meters times the cosine of 0. The cosine of 0 degrees is 1, so this should just be 85 times 6. 85 times 6 gives you a number what? 510 newtons, newton meters. Why don't we call that 510 joules? Okay, so 510 joules, 510 joules. Everybody okay with that? Okay. All right, part B. Part B is how much work does the force of gravity do on the box? Okay. How much work does gravity do on the box? Is it? It's not moving up or down at all? Okay, so yeah, let's identify this out. So we know that the work being done is going to be force times distance times the cosine of theta. So let's try this. So force, we're going to do work gravity. Okay, so it's going to be force times distance times cosine theta. And I know that these aren't parallel to each other because I know gravity like points straight down like this. Okay, so this would be mg. We know the weight of the object. We know it's 225 newtons. The angle is very important here. The angle is very important here. Okay, so we're going to type in, what is our force? Our force is gravy. Gravity? Gravy? Gravity? Yeah, right? So what is that? No. It's 9.8 meters per second squared, sure, but it gives us the weight of the box. So the force of the object is just going to be the weight of the box, 225 newtons. What is the distance that gets covered by gravity? What is our displacement of the box? 6 meters. Okay, so we're covering 6 meters. Okay, now here is the tricky question. What is the angle between the gravity and the direction of motion? What is the angle between gravity and the direction of motion? Okay, we're not looking for the angle of the incline. 5 degrees is not what we're looking for. Gravity points down like this, and the direction of motion points up like this. So we're really kind of looking for this angle, 95 degrees. So it's going to be the cosine of 95 degrees. Okay, it's the cosine of 95 degrees because that's the angle between the gravity pointing straight down and the direction of motion that is 5 degrees up the ramp. So if the ramp was flat and it's 5 degrees up, that's going to be 90 plus 5, which is 95. Okay, so it's going to be the cosine of 95. So when we do it that way, that's 225 times 6 times the cosine of 95, and that's going to give us a value of what? One 1350? Oh, okay. We got to do the cosine after 1350. Okay. So 1350 times the cosine of 95. Like you can do it in your head till you get to the cosine of 95, and then you're like, best quotes of the physics recordings. Somebody's got to have a calculator out. What is the multiplication of cosine? Like, so it's not cosine times theta. Actually, cosine, sine, and tangent are functions. So like the language of math means like for sine, cosine, and tangent, you have to have cosine of the angle of the inside. So that's not multiplication. Those are actually functions. So sine of theta means sine of 95, not sine times 95. So cosine 95 means cosine of 95 degrees, not cosine times 90 degrees. Well, sine, cosine, and tangent are just shorthands for ratios. So cosine times 95 makes as much sense as plus times 95, okay? Because cosine is a function of itself. You can add a cosine, but you can't like you can't multiply them together and expect it to be okay. Sine, cosine, and tangent are just functions. So you have to have a number in there. You can't just say sine, cosine, or tangent by itself. It makes no sense, in the same way that you can't just say plus, minus, or multiply by itself. Like if I were to just like write this on the screen, I was just like plus. Be like, congratulations, that makes no sense out of context. So you have to have numbers that go along with it. Sine, cosine, and tangent are the same way. They're functions. You have to have a number that goes along with it for it to make sense. Did y'all get a number yet? Negative 117? Okay. All right, and then we okay with the negative? Negative 117. Let's just go with joules. What, you said point 0.6? How about negative 118 joules? Okay. Are we okay with the negative? Is this okay? Try to do like the little like weird face. I don't know. How's that weird face go? Is that no, no? There you go. Are we okay with this? Does this actually make sense to us? That is cap. Okay, well, this is no cap. Yeah. Yeah, this is no cap. This is no cap because the angle right here is greater than 90 degrees, which means you are actually going to get a negative value to start with. So moving this up, it's going to be negative 118 degrees. So gravity did negative 118 joules of work, which makes sense because the direction of gravity, the force arrow points straight down, and you're making this thing go up. The arrows are opposite to each other. So when the arrows are opposite to each other, then you're going to get a negative number. So it's negative 118 joules of work. And yeah, we're okay with that. That's okay. All right. Next part, part C. How much work did the friction force do on the box? How much work does the friction force do on the box? So let's calculate work of friction, WF. How much work does the friction do on the box? Guess what? This is still force times displacement times the cosine of theta. Okay. We have a frictional force of what's it called? We have a frictional force given to us. It's somewhere. I may have to look at. Okay, you're right. It was 56 newtons, right? And it's going down the ramp. Okay, so 56 newtons. What's the distance? Okay, 56 newtons. It traveled a total displacement of 6.0 meters. And what is the angle between the force and the direction of motion? No, it is not 0. It is 180. It is flipped completely over. Okay, they are on the same plane, but it's going to be the cosine of 180 degrees. Does it come out negative? 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 Try it. Try it. What's the cosine of 180? It's like 1? What do you mean? Do you want me to? So like sometimes a picture is worth 1,000 words, and y'all probably haven't seen this yet unless you're doing some like fancy math. So I know that a lot of you, yeah, I know like a lot of y'all aren't in trig yet, right? So I'll go ahead and I'll show this to you. This is what cosine looks like. Okay, cosine, if you were to plot it over angles, looks like this. It dips down and then it dips back up again. And sometimes having this visual kind of helps out a little bit. This over here, this is all the way at 360 degrees. This is full circle, which makes sense. It has to make it back to its original location. So the cosine of 0 is 1, and the cosine of 180 is negative 1. So at 180 degrees, it's right at the other side. So this is 180. You are correct. Yeah, you are correct. Yeah. You are correct. At 90 degrees, the cosine of 90 degrees is 0, and the cosine of 270 degrees is 0. Okay. The AP Physics formula sheet has all of these handily written on the table on the back. So, like, it gives you these values. You don't have to memorize them, but that's what it looks like, okay, whenever you were to actually look at it through the whole thing. I usually, whenever I'm thinking about whether or not cosine or sine is equal to a 1 or negative 1 or 0, I try to think about what the cosine looks like on a graph, and that makes my life a whole lot easier. Because I know, hey, it starts off with a hill. It's got to be 1 at the beginning. It doesn't start off in a valley unless you've got negative cosine. Then negative cosine starts at negative 1, and then it goes up to 1 at 180. We don't got to worry about that, though. What is all this multiplied together? 56 newtons times 6 meters times the cosine of 180. 56 times 6 times the cosine of 180. Hmm. 336? Negative 336? Okay, so we got negative 336 joules of energy. And then I think we've got one more. One more to go. New phone, who dat? Yeah, spam risk. All right. The last one is, let's see here. Yeah, because I think we've done everything, right? And it says the net work done on the box by all the forces exerted on it as it moves up the incline. So what we've got to do is we've got to add all four works together. Yeah, I just didn't include one. we're missing a force. Yeah, we're missing the normal force. Now, no, it will not. Normal force goes like this, which means it's not the cosine of 95, it's the cosine of 90. So this normal force is going to do no work because it's at a complete right angle to the direction of motion. So it's zero. So even though I said we're going to add up all four forces, the work done by the normal force is zero going up the ramp. Okay? So to find the net work, we're going to add them all together. So work net equals work of gravity plus the work of U plus the work of friction plus the work of the normal. Okay? And I'm just going to go ahead and say this is zero. So we don't have to worry about OJ over here. Um, let's see. Gravity is negative 118 joules. The work that we did was 510 joules. The work of gravity, no, sorry, the work of friction is negative 336 joules. And when you add them all together, you got what, 56? What you said? 56 joules? That is correct. Very good. So we get 56 joules of energy or work being done. I shouldn't say energy. 56 joules of work being done, net work being done up the ramp. Okay. So there was a lot of forces that was at play here. One of them was the force of us pushing up. One of them was the normal force, but that one didn't matter because it was at 90 degrees. One of them was friction, and that was at 180 degrees, so it flipped it over completely. And the other one was gravity, which did a little bit of negative work, but not necessarily a whole lot of negative work. Okay? Does that kind of make sense? We're okay with that. Um, if you just did the force times distance of what? If you did like the force of us, the force of you, what do you mean the force on the object? There's four of them. Okay, if we just did the applied force times the distance, we would not get the net work done on the object. If we did force times the distance that we did, we would get 510 joules, which is the first one. That's the work done by us. Okay. Network is what happens after, like, how much work was done to actually move it up the ramp after accounting for all of the friction and stuff going away. So, like, gravity is gonna, like, some of this work gets stored by gravity, some some of this work goes away to friction. So the work that got stored by gravity, that negative 118 joules, got stored by gravitational potential energy. If we dropped it off the ramp, then that energy could come back, right? The energy that we spent due to friction was 336 joules. Okay, which what this means is that you're actually expending a lot more work to get something up the ramp than you would normally calculate in a frictionless environment. Okay. Does that kind of make sense? Because like it takes you 510 joules of energy to move this thing up, to spin the energy to move it up the ramp. But whenever you're talking about the network being done after friction and after gravity, it only really amounts to 56 joules of work. Okay, that's the network. Okay. So, are you exerting a force? Yes. Are you covering a distance? Yes. You are spending energy, but the total energy that gets spent, you won't be able to get back. And the reason you won't be able to get it back is because this work due to friction is taking that energy away. And it normally takes it away as heat or sound. Okay. Because whenever you're dragging something up a ramp, it like makes these like sliding noises. And also the bottom gets really, really hot. Okay. If you're sliding up the ramp. So that energy goes away, and because that energy goes away, the network is going to be less than the work that we actually did. Okay. Um, if it is a perfect situation, the network should be equal to the work that we did, or the work that we did plus the energy that was stored due to gravity. But since there's friction involved, it's taking away some of that energy. Okay, so this is a non-perfect situation, and we're taking into account the force of friction involved as well too. Okay, does that kind of make sense? Y'all are gonna have to be careful with me about the cosine of the angle. That's really, really doing that cosine to 95 degrees. That bothers me a little bit because I think there's a different way to do that, and I normally do it a different way. Um, so when we get to that, I will show you that different way, but I don't want to do it just quite yet. I know that it exists and I know it's there, but I'll show it to you later. And the reason why is because I want you to at least think about this way that it's a possibility, and I need you to practice it a couple of times before I show you the shortcut, easy way to do that stuff. At least for gravity, anyway. There's other ones. The other ones, the angles are important, but for gravity, we can kind of cheat a little bit. Okay. How much time do we have left? 8 minutes? Okay, what can we do in 8 minutes? Let's see here. Um, how about we've already done that. Ah, yeah, we can do this. Here's another way to write work being done, and it'll probably make you mad, and that's okay, because I don't think I've done this part yet. We have seen that force is equal to, or sorry, work is equal to force times distance, right? Okay. Well, what is force equal to? According to Newton's second law. Yeah. Yeah. So the mass of the system times acceleration. So you can write it this way as well too, and sometimes this helps, is that work is equal to m times a times d. So work can make you mad. And work does normally make people mad. Okay, just keep in mind that this mass times acceleration, that's the same thing as force right there. Okay, so really, it's totally not a different thing. It's the exact same thing. It's just that sometimes they'll give you like a mass and a distance, and they'll say like, "Hey, find the acceleration," and people freak out, and they're like, "I don't know how to do this," and it's really just that force is equal to mass times acceleration. It's not too bad. It's not too bad. Okay. And let's see here. I think uh, one more thing about kinetic energy that I didn't necessarily talk about is that it's related to the velocity squared. So that means that if you're going twice the speed, so if you go twice as fast, that's going to equate to 4 times the energy. Okay? So if you go twice the speed, you get 4 times the amount of energy. Which makes sense because like the difference between a 10 mile per hour, let's see, how about like a 40 mile per hour wreck and an 80 mile per hour wreck is like catastrophic. And the reason is because people are like, well, they're only going twice as fast. I'd be like, yeah, you're only going twice as fast, but you have 4 times the energy in that collision in order for that to happen. So you you have to be careful, okay? Because if you actually have that speed, then that's a lot of energy that you have going into that process. Another thing is you have to take into account the speed of the other person inside collisions as well too. Because if one person is going 50 and the other person is going 50, that's a 100 mile per hour collision. Because one's going 50 and the other is going 50, that's the kinetic energy of both of them going to zero instantly if they just like head on. Okay, so like that would be bad. Um, that's well, then the difference between the velocities are not as much, so it won't be as bad. However, you do have the risk of people losing control of their vehicle if you have like the because I've seen it like there's lots of times where that happens where they'll clip the car. So like the actual collision itself isn't bad, but since it's moving at like 60 or 70 miles per hour, the person that gets clipped loses control of the car, and then you have a really big problem. Okay, so like the initial collision, if the two speeds are close to each other, isn't that bad. The losing control and then hitting stuff is the bad part afterwards. Okay, so keep in mind that this kinetic energy is related to the velocity squared, and since it's related to the velocity squared, you're going to increase your energy a lot by just doubling the distance. So there is a relationship that we have to consider there that is quadratic in nature and not linear in nature. And anytime we deal with, like, human brains love linear thinking. Like, we can do linear stuff all the time. When we start doing quadratic stuff, we actually have to start thinking about it. So we've got to make sure that we're okay with quadratic. Yeah, curves are not like our brains really aren't meant to process curves. We don't like it. Lines are nice, but I think that's all we're gonna do for today because we got 3 minutes left. So I'll go ahead and stop it now.